There we go. All right, so Chemistry 102, this is chapter 15 that deals with amines and amides or amides, however you want to pronounce it. It is fine with me as long as you understand the content. Anyhow, let's start with section 15.1 that deals with amines. It says here that amines are derivatives of ammonia. When you took Chemistry 101, you had to memorize ammonia. Its condensed formula is NH3, and you probably also got some practice in drawing the Lewis structure of ammonia, which looks something like this. We have a lone pair on the nitrogen, and it has 3 bonds to hydrogen. If you wanted to draw the molecular geometry correctly, you would draw it as a trigonal pyramid. So remember trigonal pyramidal. So you'll have 1 hydrogen going in the back like this, and 1 coming out in front like that. And the bond angles in ammonia are a little less than 109.5 degrees. They're closer to around 107 degrees, and there's a good reason for that. Well, amines, which again are derivatives of ammonia, are the most important type of organic base found in nature. Although amines are bases, they are weak bases. Okay, if you think of a strong base, you think of something like sodium hydroxide, right? Sodium hydroxide is a really strong base. Okay, but amines, they are bases. However, they are weak bases. So there we go. Anyhow, again, if we consider them as a substituted ammonia molecule, we can have what's called a primary amine, a secondary amine, or a tertiary amine. And all that is, it's based off of the number of R groups. If you have 1 R group on your nitrogen, you've got a primary, so 1 R group and 2 hydrogens. Right? If you've got 2 R groups and 1 hydrogen, then it's secondary. And if you have 3 R groups, then your amine is tertiary. So you have to know the difference between a primary, a secondary, and a tertiary amine in this class. Very important that you know the difference between those. If you take a look at that molecular geometry of ammonia in an amine, now more correctly than it is drawn here would be to put a wedge here, for example. On this one, let's say, that's not a very good wedge, is it? To fix that up. We put a wedge like this, and then we put a dash to show that one's going in the back, and then we could do something similar here. And if you're unsure about the trigonal pyramid, right, the trigonal pyramidal structure, you could make a model of that in the lab. We have atoms that represent nitrogens, we have lone pairs, we have hydrogens, and so you could make a nice model, and you could see that the bond angle here is close to 109.5 degrees, but it's a little less than 109.5 degrees, a little less. Anywho, if we move on again, this is just another slide. I took this straight from our textbook. It shows the classification of amines. Again, you need to know the difference between ammonia, which is NH3, a primary amine where we have 1 R group, a secondary amine where we have 2 R groups, and a tertiary amine where we have 1, 2, 3 R groups. You got to know the difference between all of those. And I know that all of you have completed lab number 1, and so you actually get some practice in making some models of amines. And so you might remember making a model similar to this one of methanamine or methylamine, which is a primary amine. And you see that we have the nitrogen that has 2 hydrogens attached to it, and it's got 1 R group, right? That methyl group is considered an R group. If we have dimethylamine, which is what's shown here, we have the nitrogen with only 1 hydrogen attached to it, right? And we have 1, 2 R groups like that. And then a tertiary amine, we have the nitrogen and we have 1, 2, 3 R groups. All 3 of them are methyl in this amine that is called trimethylamine. All right, well, there's some really interesting differences between ammonia, primary, secondary amines, and tertiary amines. Anyhow, but before we get into those, I want to talk to you a little bit about hydrogen bonding. Right? It says here that amines can form hydrogen bonds, but they're not as strong as alcohols, and there's a really good reason for that. It says that nitrogen is less electronegative than oxygen. If we think about the requirements for hydrogen bonding, we've gone over this probably 10 times in this class, okay? The requirements are either a bond between oxygen and hydrogen, nitrogen and hydrogen, or fluorine and hydrogen, like that. If you compare the difference in electronegativity between oxygen and nitrogen and hydrogen. Oxygen has an electronegativity of 3.5, hydrogen is 2.1. Nitrogen is 3.0 and hydrogen is 2.1. So the difference, the delta in electronegativity between nitrogen and hydrogen is 0.9, whereas the difference in electronegativity between oxygen and hydrogen is 1.4. And so the dipole between hydrogen and oxygen is stronger. That means there's more of a delta negative charge on the oxygen and more of a delta positive charge on the hydrogen in an oxygen hydrogen bond compared to the delta negative and the delta plus in a nitrogen hydrogen bond, because those partial positive and partial negative charges are a result of the difference in electronegativities between those two elements, right? Whether it's a nitrogen hydrogen or an oxygen hydrogen bond. All right, if we go back here, you see that ammonia has nitrogen hydrogen bonds. It's got 1, 2, 3 of them. If you look at a primary amine, you see that it has 2 nitrogen hydrogen bonds, and a secondary amine has only 1 of them, whereas a tertiary amine has no nitrogen hydrogen bonds whatsoever. And so that tells you that a tertiary amine is incapable of hydrogen bonding, whereas all 3 of these here can form hydrogen bonds. And we know that hydrogen bonding is the strongest type of intermolecular force. All right. So again, tertiary amines cannot hydrogen bond to each other, and the reason why is because they have no NH bonds. They don't have any. So if they don't have an NH bond, then they can't form a hydrogen bond. Here is hydrogen bonding. So this is H bonding between molecules of methylamine. So methylamine, which is just this, a methyl group with a nitrogen and 2 hydrogens bound to it. Okay, that's what they're showing here. All right, just like we did when we showed hydrogen bonding for alcohols. We draw the hydrogen bond between the delta plus on a hydrogen atom and the lone pair. It looks like it's connecting here to the nitrogen, but technically we usually show it to a lone pair. So let's say I was to draw another molecule of methylamine in here. I'll just draw one here like this. You have the 3 hydrogens attached to the carbon. Okay, you have the nitrogen. You have a lone pair. You have a hydrogen here and a hydrogen here. And then to show the hydrogen bond, you show it like this, right, between the delta minus on the nitrogen and the delta positive on the hydrogen. If we had a secondary amine, let's say we had dimethylamine here. I'll just draw a condensed structure. Maybe I'll try to be consistent with my colors here. So let's say we had a secondary amine like dimethylamine. It's got a nitrogen-hydrogen bond, only 1 of them. Okay, we could draw a hydrogen bond. Let me move my lone pair maybe over to this side. And we could draw a hydrogen bond between this hydrogen and this nitrogen, right? So this one here, and that's just to point out there's 1. This is a secondary amine, okay? But again, in a tertiary amine, we cannot find any hydrogen bonding because there's no nitrogen-hydrogen bonds. Well, since the dipole between nitrogen and hydrogen is lesser than that dipole between oxygen and hydrogen, it tells us that the hydrogen bonding in amines is going to be weaker than the hydrogen bonding in an alcohol. If we compare the boiling points of these 3 compounds here, right, we're comparing an alkane, which is propane, comparing the alkane with a primary amine and an alcohol. Okay, well, you can see that they all have very similar molar masses. They're all around 45 grams per mole, give or take. But you see there's a wide range of boiling points going all the way from -42 up to almost 80 degrees. And then you have the amine somewhere in the middle around 17 degrees Celsius. Now, why is that? Well, the only intermolecular forces experienced by an alkane are London forces. London forces. The ethanamine and the ethanol, both of these here, they both experience London forces. They both experience dipole-dipole forces, but they also possess hydrogen bonding in both of them. Okay, there's hydrogen bonding here and there's hydrogen bonding here. But the hydrogen bonding in an alcohol is stronger. So if we just write stronger hydrogen bond. That's all there is to it. Again, the primary amine can hydrogen bond, it's just not as strong. And so tertiary amines, of course, are going to boil at a lower temperature than primary secondary amines of the same molecular weight. Why would that be? Because they can't hydrogen bond at all. Again, if we look at these three compounds down here on the bottom, they all have the exact same molar mass. They're all isomers of each other. Okay? The first one, propanamine, is a primary amine. The second one, ethylmethylamine or N-methyl ethanamine, is a secondary amine. And the third one is trimethylamine, and that is a tertiary amine. Again, these two here can participate in hydrogen bonding. Okay, so that's why they have significantly higher boiling points of, around 49 and 37 degrees Celsius compared to this guy down here, which boils at only 3 degrees Celsius. That's the temperature outside on a pretty cold day. Okay, it's already going to be converted to a gas. Why? Again, because there is no hydrogen bonding, okay, in a tertiary amine. All right, there we go. Now I have a question. Why do you suppose the primary amine has a higher boiling point than the secondary amine? Can anybody answer that? Give me an inkling as to why that is. Exactly. Alexandria nailed it. It's because it's got two nitrogen-hydrogen bonds, right? The primary amine has two nitrogen-hydrogen bonds, whereas the secondary amine only has one of them. And that's the answer right there. More capability for hydrogen bonding, higher boiling point, right? More intermolecular forces. Here's a table that comes straight out of our textbook. If you compare, and you can kind of break this table up any number of ways, but the way that I would do it is to compare, let's say we compare these three right here. Okay, all three of these compounds, N-dimethyl, methyl, methanamine, ethanamine, and propanamine, they all have the same molar masses. They're the ones that were on the last slide, right? What happens if you increase the molar mass? If you go from propylamine to butylamine, right? You just add an extra carbon on it. Well, of course, the boiling point is going to go up, right? Compared to 48.7, it increases. Why? Because it's just a heavier compound, more intermolecular forces, nothing more than that. All right, we spent quite a bit of time on that. If you compare the relative boiling points of alcohols and amines, so methanol is CH3OH, and methanamine is CH3NH2. They both have a very similar molar mass. However, they have a huge difference in boiling points. Why? Because the H bond is stronger in an alcohol than an amine. Okay? We see the exact same thing here with ethanol and methanamine. Ethanol would be CH3, CH2OH. Ethanamine would be CH3, CH2, NH2. Again, same thing. H bond stronger. Shit, did I put it in the wrong one? Yeah. Stronger. So I'll move that up. That should be next to the alcohol. There we go. All right, and then the exact same trend is seen here between propanol and propanamine. All right, if we compare these molecules, just ask us which one will have a higher boiling point. Now, we haven't covered the nomenclature of amines yet, but I'll help you out. Methanol is just this. Everybody knows the structure of methanol. And if I compare it to methylamine, well, if we go back, you can see that those were on this slide right here. Methanamine is the same thing as methylamine. And so methanol is going to have a higher boiling point because of the stronger hydrogen bonds. Let's go to the next one. It says you compare dimethylamine or water. So dimethylamine is this. If you have CH3, NHCH3, and then H2O, everybody knows what water is. Well, water is going to have a much higher boiling point because water has more capabilities for hydrogen bonding, right? And the hydrogen bonds are stronger, right? The oxygen hydrogen bonds are stronger than the nitrogen hydrogen bonds. The next one is methylamine or ethylamine. So methylamine would be this, CH3, NH2, you know that by now. And ethylamine would be this. Oops. Now we kind of went over this on the last slide. And the compound that's longer is going to have more intermolecular forces, and therefore it's going to have a higher boiling point, right? Just increased London forces. And the last one is propylamine, which would be this. So if you had 1, 2, 3 propylamine, or 1, 2, 3, 4 butane. Well, obviously the amine is going to have a higher boiling point. Why? Because it has the capability of hydrogen bonding, and the alkane butane does not have that capability. So you can see how these kind of questions lend themselves to a multiple choice question on an exam very easily. What about solubility of amines? Well, if amines can form hydrogen bonds, then they can absolutely form a hydrogen bond with a water molecule. That tells us that since we know the rule that like, right, this is a general rule in chemistry, like dissolves like, that means if something can form hydrogen bonds, it should dissolve in something else that can hydrogen bond. Right? So if we have amines that are up to 6 carbons, okay, up to about 6 carbons, they're going to be soluble in water on account of hydrogen bonding. Here is hydrogen bonding shown between, this is methylamine. You can probably guess where that name comes from. You get a methyl group and you have an amine. Okay, so methylamine and water. But what happens is, as we increase the length of the hydrocarbon portion of the molecule, the water solubility is going to decrease, right? Basically, the hydrophobicity, or the water hating portion, the hydrocarbon portion or tail of the molecule, is going to negate any hydrogen bonding capabilities, right? Let's say, for example, you had something like this. Say we had 1, 2, 3, 4, 5, 6, 7, 8 carbons, and then we have a primary amine. Well, yeah, I would agree that this part here can hydrogen bond, but this non-polar hydrophobic portion is so big that it's just going to cancel out or negate any of the solubilizing effect that the nitrogen hydrogen bonds will have. Okay, so the rule is, you want to know what the summary is, up to 6 carbons means generally are going to be water soluble. That will be the rule for our class. Are there exceptions to the rule? Probably. We're not interested in every single exception under the sun. Well, let's get into the nomenclature of amines, which can sometimes be a little daunting. I'll give you a heads up. Naming primary amines isn't very challenging for most students, because if you understood the naming of an alcohol or a ketone or an aldehyde, usually naming a primary amine isn't that difficult. Okay. Once we get into naming secondary and tertiary amines, that's when it gets a little more interesting. So how do we name a primary amine? You can probably guess what the first step is going to be. We find the parent compound. But instead of just finding the longest carbon compound, like we did with alcohols, we have to find the longest carbon compound, the longest carbon chain that contains the carbon with the amine group on it. So we've got to have the nitrogen attached to a carbon on that chain. Then you drop the final E in the parent name and you add amine to the end. So if you had, let's say, butane, let's say you had 4 carbons, you drop the E and it becomes butanamine. Okay? If it was pentane, it would be pentanamine, hexanamine, heptanamine, octanamine, so on and so forth. Then, how do you number the longest chain? How do you number that parent? You number it so that you give the carbon with the nitrogen attached to it the lowest possible number, right? Just like we did with alcohols And then we just name and number everything as usual. So now, if I have just a methyl group, like is shown here, well, there's no locant, there's no number that I need to provide because there's only one carbon anyway. So instead of being, right, if you had CH4 rather, this would be methane. And so what do? We cross off the E and we put methanamine. Okay, if you had CH3, CH2, CH3, you would call that propane. You drop the E, you get propanamine, but we have to number it 1, 2, 3, and we get 1 propanamine. Why do I have to give it a number? Because why couldn't you have this? Why couldn't you have the nitrogen on the second carbon like that? If you had this, then you would have 2 propanamine. All right, and lastly down here it says we have 2 pentanamine, and I think you probably get the idea. If you have pentane, you drop the E, it becomes pentanamine. And if you number this chain 1, 2, 3, 4, 5 in a way to give the carbon with the nitrogen the lowest possible number, it becomes 2 pentanamine. So that's naming primary amines. Okay. When it gets to secondary and tertiary, like I said, it gets a little more interesting. But like a lot of things in organic chemistry, there's more than one way to do it. Okay, there's a common way, and there's also a systematic way. So what we do when we have a secondary or tertiary amine, we prefix, or the prefix N-alkyl is added to the name of the parent for secondary and tertiary. Now, if you're wondering, what the heck is N-alkyl? What does that mean? It means you put the letter N, and then let's say you had a methyl group, you'd say N-methyl. Or let's say you had N and then you had it attached to an ethyl, it would be N-ethyl. Or N, let's say you had an isopropyl, isopropyl. Okay? And then we'll put etc. We'll see several examples of that. So, if you're wondering, where does this name come from here? Let me show you. If you had this, CH2, CH3, right, NH2, what would that compound be called? That would be called ethane amine. Okay? Now you can see that in this compound that's shown here, the longest carbon chain are these 2 carbons here. But we have, this is the N-alkyl group, the smaller group. So this is smaller, therefore it is the N-alkyl. And what is it? It's a methyl group. So that means it's going to be an N-methyl, and then I add ethanamine. So N-methylethanamine. This one over here on the bottom right, look, the longest carbon chain only has 1 carbon, right? So if I had just 1 carbon and my nitrogen attached to it, what would that be? That would be ethanamine, right? Okay, well, if I have 2 alkyl groups, I have to write the nitrogen capitalized, italicized. Obviously, you're not going to italicize it if you're writing it with a pencil, but normally in text it's typed, it's italicized. So you put NN, so 1 N for every substituent, okay? And then since we have 2 methyl groups, it's going to be dimethyl, so NN dimethyl methanamine. Okay, a little tricky. What about an aromatic amine? Okay, now you guys have all learned the structure of aniline. This is one of the aromatic compounds I asked you to memorize the structure of a long time ago. If you have a primary amine, so an NH2 group on a benzene ring, it's called aniline. Now, aniline is the common name. You know what? I've been studying organic chemistry for 25 years or something. And if somebody was to say to me benzenamine, I mean, I know what it is, but I would never say that, okay? In my everyday language, everybody calls it aniline. Well, what happens is if you add additional groups, you get some interesting different common names. So the names that are shown here is, what if you put just a methyl group on an aniline ring? You guys probably remember the structure of this molecule here. I'll draw it up in the top left-hand corner. If I have an aromatic ring with a methyl group on it, it's called toluene, right? That's one of the aromatic compounds that I get you to memorize as well. So if you have a toluene molecule with a primary amine, it's called toluidine. Kind of a weird name, and it's a common name, but it's very common. So if the 2 groups are 1, 2, 3 apart, that's meta substitution, this would be metatoluidine. If they're 1, 2 apart, that would be orthotoluidine. And if they're 1, 2, 3, 4 apart, then we have paratoluidine. Okay, that is something that you would need to know for the next exam. Okay, for your next exam, I would not ask you about toluidine on the final, or at least I've never done it. Okay, but you should know what a toluidine is. Anyhow, common names of amines. You know, organic chemists love common names, right? They love to have a sweet common name for everything just to make things a little simpler. If you have a small amine, that's really the only time we use common names a lot, I would say, in organic chemistry, is students love the common names of amines because it's very intuitive. All you have to do is name the alkyl groups attached to nitrogen in alphabetical order, slap the word amine on the end, and you're done. Let me show you. If you have a methyl on your amine, you call it methylamine. If you've got 2 methyl groups, what would it be? Dimethylamine. What if you had an ethyl group? Ethylamine. Now, what if you have an ethyl and a methyl? Well, the letter E comes before M in the alphabet, and again, it's in alphabetical order. So it would be ethylmethylamine. What about this guy over here? Trimethylamine. Okay. Let's say, for example, if we just made one up, let's say you had a propyl group over here and an ethyl group and a methyl group. You've got ethyl, methyl, and propyl. So we write those down. We've got ethyl, we've got methyl, and we've got propyl. What's the order they come in? We have E before M and then P. And so this compound would be called ethyl, ethyl, methyl, propyl, amine. And if you're thinking, I like that. Yeah, absolutely. Common names for amines are really nice. Okay. And they're commonly used. Okay? They're used to this day. I promise you, you're not learning this for nothing, you know. If I was going to ask another chemist for trimethylamine, I would definitely say trimethylamine. I can't imagine the circumstances under which I would say N,N-dimethylmethanamine. Somebody would look at you like you're crazy, okay? I mean, any good organic chemist will know what you're talking about, but they'd be like, what are you saying, you know? That's weird, okay? Where did you go to school or something? Anyhow, I'm going to skip the part about amphetamines right now. I have some information about that. The videos for chapter 15 videos, I talk all about sulfa drugs and Sudafed and ephedrine and all these different things. But I want to get into reactions with amines. How would you go about making an amine, right? What's something you might do to make an amine? Well, one of the easiest ways to make an amine is to do a reduction of a nitro compound, okay? A reduction of a nitro compound. And, oh, is that not what I have there? Oh, reduction of an amide in a nitro compound. Sorry, I didn't read it carefully enough. Anyhow, so reduction of an amide. Well, what's reduction in organic chemistry? It means what? It means loss of oxygen and or gain of hydrogen. So if we take an amide and we treat it with a source of hydrogen, so when we put H like this in brackets, all this means is reduction conditions. And if you're like, why don't they tell me exactly what they are? Well, they can really differ depending on the situation. But if we reduce an amide, what are we doing? We're losing the oxygen, right? That's going away, and we're gaining 2 hydrogens. That's definitely a reduction, isn't it? So again, if we treat an amide to reduction conditions, we can make an amine. If you're wondering what a nitro is, a nitro looks like this, RNO2. This is a nitro. And if we do something similar, if we treat it with reduction conditions, we're going to get rid of those 2 oxygens, and we're going to replace them with 2 hydrogens. Okay, so a nitro to an amine. And here we're reducing a nitro to a primary amine. Anyhow, there you go. And that's shown down here at the bottom. Where do we get aromatic amines? You know, like like aniline, or maybe a toluidine. Toluidine. Okay. Where do they come from? If you take a nitro compound and you reduce it again with some kind of reducing agent, you can make an aniline derivative. There we go. So that's one of the a couple good ways to make an amine, whether it's an aromatic amine or an aliphatic amine. Well, if you go back to the first slide that we talked about tonight, the first or the second slide, I said that amines are bases. They're weak bases, right? What's the definition of an acid and a base? If we go back to our Bronsted-Lowry definition, an acid is an H plus donor, right? A proton donor, and a base is an H plus acceptor. Well, if an amine is a base, that means it's going to accept a proton when you put it in water. Let me show you. Here's my primary amine, right? This is just some generic primary amine, and here's a water molecule. They've highlighted this bond on purpose. Okay, there's a reason for it. Because literally, and this is no joke, what happens is the pair of electrons on the nitrogen actually form a bond, okay, to that hydrogen. That's what that curved arrow represents. Bond being formed, okay? And then what happens to the pair of electrons in here? That bond is going to break, and the pair of electrons is going to go on here. And so that represents, this one represents bond being broken. Okay, so we've got bond being formed and bond being broken. Now we've got an alkyl ammonium ion. Okay, and we have a hydroxide ion. You should absolutely know the name of hydroxide from your chemistry 101. You hopefully remember this. When you have NH4 plus, that's called ammonium. So if we replace one of the hydrogens with an R group, it becomes an alkyl ammonium. All right. And if the R was aryl, it would be an aryl ammonium, but anyhow, an alkyl ammonium. I can't stress this enough that you've got to understand how an amine behaves as a base in water, that it accepts a proton and it produces a hydroxide ion. Here's just a simple example of an amine acting as a base in water. Let's say we have some methylamine and we put it in water. What's going to happen? You're going to form a bond between the nitrogen and one of the hydrogens from water. And then this bond is going to break, and those electrons are going to go onto the oxygen to produce the hydroxide. Notice that we have reversible arrows. And when we have reversible arrows, what does that mean? It means equilibrium. Equilibrium. Okay? And the reason why we have to use equilibrium arrows is because of weak base. If it was a strong base, sure, you draw the arrow irreversible like that, but since it's weak, we draw it in an equilibrium. Another important reaction that you got to understand is a neutralization reaction of an amine. Think back to your general chemistry. If you took a base, like sodium hydroxide, and you treated it with a strong acid like hydrochloric acid, what happens when you mix an acid and a base? You get a salt, like sodium chloride, plus water. Well, here's the exact same thing. An amine is a base. If we treat it with an acid, what do we end up with? Now here we don't get water, but we end up with a salt. It's an alkyl ammonium salt, but it's still a salt. Okay? Now how does that happen? If I show you the curved arrows, and this is literally what happens, the pair of electrons on the nitrogen forms a bond to the hydrogen, and the pair of electrons that's shared between the hydrogen and the chlorine goes on the chlorine to make chloride. So that's how we end up with our alkyl ammonium salt. If you've ever wondered why people put lemon juice on fish, it's not just because it's delicious. Historically, when fish were caught and before modern refrigeration techniques were invented, the fish would decompose over time. And when fish decompose, the smell that you're smelling of stinky, like rotten fish, are amines. And so when you put lemon juice on an amine, which is volatile, which means it can turn into a gas, and that's why you smell it. If you put an acid on it, it makes a salt, which is not volatile, which doesn't boil, which doesn't turn into a gas. And so it eliminates the odor of rotting fish. So that's one of the ways that people mitigated the odor of fish that would decompose over time. Anyhow, naming an alkyl ammonium salt, we name those alkyl ammonium salts that we've seen on the last couple of slides by replacing the suffix amine with ammonium. So instead of methylamine, let's say it'd be methylammonium. Instead of ethylamine, it'd be ethylammonium, so on and so forth. And then we just throw in the name of the anion, chloride, bromide, iodide, whatever it is. So converting amines to salts makes insoluble amines more soluble because salts are ionic, right? If you have a salt, it consists of a cation and an anion, and so this is going to be water soluble, right? Whereas maybe an amine is not soluble. For example, if you convert it into a salt, oftentimes it will render it soluble. Let's take a look at this name here. We have methylamine. We talked about how to name a primary amine. Okay, that's not new. But where does this name come from? We drop the word amine. We replace it with ammonium. So we get methylammonium. Our anion is chloride. And so we get methylammonium chloride like that. Now, what can you do with an alkyl ammonium salt? You can neutralize an alkyl ammonium salt with a hydroxide ion. And the reason why you can do that is because an alkyl ammonium salt is, in fact, a weak acid. So it's a weak acid. That means it can donate a proton, right? Because acids, right? Acids donate H plus. Okay, so if we take an alkyl ammonium salt and we treat it with hydroxide, what's it going to do? The hydroxide is literally going to yank a proton from the alkyl ammonium salt, and this pair of electrons, where's it going to go? It's going to go back onto the nitrogen, like that, okay? So we end up with an amine and water. And the reason that this is so important, okay, this back and forth, right, because we saw that here we could protonate the amine to make an alkyl ammonium salt. Then we're taking the alkyl ammonium salt and we're deprotonating it. So if you're wondering, why would you do this? Why would you protonate it and then deprotonate it, right? You're starting it with, and did I erase something I didn't mean to erase? Yeah. You're starting it with an amine here, and then you're ending up with an amine at the end, Mr. Dion. What's the point? Well, the point is that when you ingest a drug, most drugs that are prescription drugs contain nitrogen. And in order for them to cross things like the blood-brain barrier or the intestinal walls or to, pass through the stomach or into the intestines, depending on where they might be in the body, you'll want the drug to either be in the protonated or deprotonated form, depending on the situation. And so the human body can actually take advantage of the fact that an amine can exist as a protonated or deprotonated form, depending on where it is in the body. A quaternary ammonium salt, we call these quats. I'm not going to ask you a whole lot about a quaternary ammonium salt. A quaternary ammonium salt is when we have a nitrogen that's got 1, 2, 3, 4 R groups bound to it, a positive charge, and then it has some kind of anion. Okay, and the anion is most likely a chloride, is what it says here. So let's just throw in a chloride for fun. Okay. Now, if you're wondering what's the significance, Mr. Dion, of a quaternary ammonium salt, okay, great, I have a nitrogen with 4 R groups. Wow, great, whoop-de-doo. Well, the cool thing about quaternary salts is they can be used as disinfectants and antiseptics. So that's about what I would ask you for that. But if you look at things like benzyl alkonium chloride and cetylpyridinium, I think one of these, I think it's this one here, is found in things like Scope mouthwash. So it's used as an antiseptic in your mouth, when you rinse your mouth out. But that's generally what quaternary ammonium salts are used for. Choline is this molecule here. I'm not going to ask you to memorize the structure of choline, for the upcoming exam. However, choline is going to show up quite a bit in the biochemistry portion of this course. So after spring break, you're going to see the molecule choline show up a couple of times in some other chapters. So you'll see quaternary ammonium salts show up again. But again, for the next exam, it's just wise that you know that quaternary ammonium salts are widely used as disinfectants and antiseptics.